Thank you for the presentation. Hello, everyone. First of all, I would like to thank the previous speakers, because I think that even though there was no deal, they touched very important aspect in the behavior of concrete, fiber-reinforced concrete, and UHPC at high temperature. And so I hope that with this presentation, starting from those hints, we try to add another brick to the wall. In fact, in this study, we will face specifically the residual condition, so after the fire, looking if there is any effect on the timing from the extinguishing of the fire. So why UHPC? With Professor Kodur, we already saw interesting application. Here there are other that are very, very interesting, in my opinion. For example, on the left, we see a bridge. It is a pedestrian bridge in Spain, realized by a company, RDC, that has been partner of Politecnico Milano in a few projects. Is made by UHPC, pre-stressed one. And then we have other applications in which typically we don't use UHPC, maybe HPC or fiber-reinforced concrete, but anyway are interesting for what we are discussing today. And also other kind of tunneling or underground structures for services, for facilities, and so on. And then regarding building, we have also the big sector of strengthening with the jacketing of UHPC. So it's important to say that the tensile behavior also under direct tension is becoming more and more important. So we cannot just speak about bending, but we have to move to tension to understand how this happens. Because for example, especially in this case, where we have jacketing, and so the confinement of the concrete inside, and also in this case, we have members that are subjected to tension, to direct tension. The market of fiber-reinforced concrete is also increasing thanks to the pushing ahead of the tunneling and infrastructures. So this is the reason why I mentioned this application before. And in these cases, so the problem is not only the compression, obviously, but also tension, and especially what happened in the residual condition. So to understand if some rehabilitation or some strengthening had to be performed in the structure. So starting from what we said, what we saw in the previous speech that was very, very interesting, here I start from what the standards, I mainly make reference to EC2, said about the hot mechanical performances. So we are speaking about the performance of the material during heating. Here in the graph, we can see in red the curves referred to compression. So this is the relative decay with the temperature of the compression. We have two curves because this one refers to what I called here normal strength concrete, in the sense that the Eurocode makes reference to compressive strength lower than 70 megapascal, and then to concrete with a compression higher than 70 megapascal. So it does not make reference to UHPC. Maybe it's more like the HPC, but anyway, we can imagine to be here. So this curve represents what EC2 suggests for high-performance concrete. This is this decrease here. It's the opposite that Dr. Wiley showed before. Why this happened? Because in that case, we were looking at the residual condition, so after heating, while this is what EC2 meant for hot condition during heating, so the difference is the vapor pressure. In this range, we have a lot of pore pressure. This means that we have tension inside concrete due to the pushing of the vapor. And so we have a decrease of the compression that we can measure during the hot test. So this is a quite tricky phenomenon, because typically what happens if we measure the compression in residual condition and to see a gain in compression because of the rehydration or hydration, it is like a hot curing in the end if we remain at 200, 300 degrees C. An important aspect is the Young modulus, or the elastic modulus. Eurocode 2 does not give the decay of the Young modulus, but it gives us the constitutive law for any temperature. So by just calculating the slope at the beginning, we can work out the elastic modulus. Pay attention that it's not correct to use the term elastic modulus, because during heating, we don't see just instantaneous deformation, but we see also creep. And the problem of high temperature is that creep is strongly fast. So in the few hours in which we have heating, we see the creep effect that they can double or even more the deformation within concrete. So what we see here is a strong decrease of the Young modulus, because since Eurocode 2 takes into consideration also thermal creep, we have a further decrease of the deformation. Finally, going to the green line, we have the decay of the tensile strength. This line is given by the Eurocode 2, in which practically they give the same curve for the cracking stress of the matrix and for the tensile strength of the fiber-reinforced material. So there is this, while in the FIB Bulletin 83, this is the only curve that refers to these guidelines, in which the tests were performed directly aiming fiber-reinforced concrete, we see that this curve is more conservative than this one. So it is interesting to understand if the suggestion given by the EC2 can be more or less appropriate than what the FIB bulletin does. Also because in general you see that moving from the circle to the square, we move from lower grade concrete to higher grade concrete, we have a decrease for the Young modulus and also for the compression stress, while the opposite we have for tensile stress. So we have to understand if this works. We have to remember that this is for hot condition. The UC2, here it's wrong because it's written 2004, but this is the last Eurocode, so 2023. And for the first time, Eurocode try also to give the information for what's happening in the residual condition, because during the cooling down of the temperature, we have a further increase, not so much, but we have a further increase of the damage because of the relaxation of the irreversible strain accumulated during heating, and so we have further microcracking. In general, as you can see here, in this square, we have what is referred to the normal strength concrete, and here to the higher grade concrete, so we can say HPC. You see that KT is the decay of the strength with the temperature, while phi, from this perspective, it's not easy to see, while phi represents the further decrease because of the cooling phase. You see that this coefficient in the end is between 0.9 and 1. So in the end, the Eurocode is more or less saying that the residual condition, in the residual condition, we have almost the strength related to the maximum temperature reached in that point. This is quite tricky, especially for structural analysis, because in structural analysis, the properties in any point of the material do not depend anymore in the actual temperature. So at 5 hours, the temperature is this one, so I know what is the compressive strength. No, because I need to know what was in that point the maximum temperature reached. This, for the structural analysis, is much more complex, because so far there is no software that allows to perform this kind of analysis. So here, just to show the analysis that we perform comparing two structural solutions for a deep tunnel, we implement a routine in Abacus in order to make the properties of the material depending on the maximum temperature reached up to the moment of analysis. And so we have to define also that during heating there is a decrease of, for example, here the compressive strength, but if I have cooling, I don't have a gain of the compressive strength, but I have to move horizontally because I leave the damage that I reached at that moment. So this slide was to show you a practical application in which residual conditions are very important, because in this tunnel we perform the structural analysis, taking into account also the cooling phase. And what you observed is that in the plot you see that in the first 3 hours we have the heating phase. After the vertical red dashed line, we have the cooling phase. And in these cases, with both structural technologies, we have that the least value of the safety factor was reached far after the maximum temperature reached during the flight. That was after 3 hours, so during the cooling phase. The cooling phase is very important because we have the fire brigades that are working often, and these anyway give us idea of what the safety factor of a structure that overcome a fire. There is anyway a positive news that I can say to you, that is during the, not during the cooling phase, but after cooling, with the time passing through, we have an important phenomenon that is self-healing. Self-healing is induced, is a phenomenon taking place especially in the cracks, thanks to the formation of, you see here on the top left, calcium carbonate, and also the continuous rehydration of anhydrated cement particles. Because you know that in HPC and UHPC, we have a lot of binder that is not hydrated. And so during heating sometime, and this explains the gain of strength between 200 and 300 degrees C. And then in the residual phase, so with passing of the days, we have the hydration of this particle, and so we have a recovery of the material properties. So now let's go to the study. On the table we can see the mixed design of the UHPC we adopted. You see that there are 700 kilos of cement. The amount of fiber is not so high, even though we are 1.3% by volume fraction, but we also have polypropylene fibers, which aim was not to increase the tensile strength, but just to try to avoid spoiling. We had the spoiling in our furnace. It was not with this mix, with a UHPC, another UHPC mix, and it was not a very good idea. But no one was hurt. The heating is very slow for the reason discussed before. So because we don't want to have thermal gradients inside the specimen, because we want to assess the material behavior and not the structural behavior, because with thermal gradients we introduce also stresses that depends on the geometry of the specimen. Then we maintain the temperature for 1 hour or 2 hours, I don't remember. And then we have a cooling that was very slow, less than 1 degree C per minute. So it's not an easy table, but summing up, what we did is we have specimens that have been heated without any pre-cracking. Then we have specimens that have been heated, but before heating, we pre-crack the sample. And then there are samples that have been pre-cracked, heated, then we wait 6 months and we perform the test. So in this way, we see the effect of pre-cracking before the heating process, and the effect of the timing starting from the cooling of the specimen. So on the 3 sets of samples, the third one was meant to study the self-healing effect in the 6 months after the end of the thermal treatment. It's important to say that the curing during the self-healing was underwater. This led to an overestimation of the self-healing. So if we had the chance to continue with this experimental campaign, the idea could be also to see what happened in other curing conditions. We stopped at 400 degrees C. This is important because also Dr. Wiley discussed in his presentation the chemical processes that takes place in concrete takes place from 100 to 1,200 degrees C. But the large share of the irrecoverable chemical processes start at 450 because we have the decomposition of the calcium carbon, of the portlandite. So starting from 450, the concrete start to be damaged and seriously damaged, and during the cooling we don't have important recovery. So typically we have to remove the concrete that overcome that temperature. For lower temperature, we will see that there is chance for keeping concrete as it is because it can recover the properties. Regarding steel, so the steel of the fibers, steel typically for this range of temperature, when it is cooled down, it recovers all the parameters. So from steel side, we are on the safe side. Okay, here there is the description of the experimental campaign that I try to depict as clear as was possible. I would like to add just that we perform also ultrasonic measurement, because the ultrasonic measurements are non-destructive, so we can follow the evolution with time, and the ultrasonic pulse velocity give us an indication about the stiffness of the material. So let's go on the test. We performed flexural test. You see that the samples are a little bit different from what shown in the standard, because we are dealing with thin beams. This is a typical test that we perform in Milan. Just to focus here, you see that on the left we have the response after the thermal treatment for specimens that have not been cracked before. On the right, we have the behavior of the specimen that have been pre-cracked before the thermal treatment. You see that we have differences. We have important differences in the maximum strength that we can reach. So we have an influence of this, and this can be an information to be taken into account when we perform the characterization at high temperature of concrete material. So here, trying to summing up, on the left, the gray rectangle refers to reference concrete. So you see that we have some scattering, while the yellow one represents the results after heating. So you can see that if we do not perform any pre-cracking, we don't have damage, okay? So practically we have the same value of cracking of flexural strength than before heating. If we if we apply pre-crack, we have a more important decrease. This is more evident at 400 degrees C, because moving from uncracked sample to pre-cracked sample, you see the decrease is much more. What is the last rectangle? So this one and this one. This is the behavior after 6 months of healing, curing underwater. So you see that we have a recovery of the tensile strength. How this can happen? Because we have the closure of the cracks. We have also the reduction of the dimension of the pores, and we also have a recovery of the bond of the fibers and the matrix. I didn't stress this in the tables of the mix design, but in the mix there is also a penetron admixture that is a crystalline admixture that fosters the closure of the pores, because it is a reactive material, and so it reduces the permeability, and this emphasizes the effect of self-healing. We perform a similar study also for the stiffness, but I don't want to, I prefer to move to the summing up, that is some slide later. This is what we get with the ultrasonic pulse velocity measurement. So we can see here that we split the effect of the pre-cracking. So just for pre-cracking, we are damaging concrete, so we have a decrease of the pulse velocity of 16%, while if we hit an uncracked specimen, we have a loss of 5%. This means that the loss of the damage induced by pre-cracking is even more than the damage induced by heating. If we if we pre-crack and we heat, we have a loss between 11 and 21%. So in the end, a good estimation is the summing up of these two contributions. Then the same for 400 degrees C, but obviously in this case we have a far larger damage, and so the difference between uncracked and pre-cracked sample is less evident. Here, let us focus on what happened after 1 month, 2 months, 3 months, and 6 months. You see that we have a recovery of the properties that is quite faster, because after 1 month we already have a good recovery. Pay attention that the elastic modulus is proportional to the ultrasonic velocity to the second power. So these differences should be elevated to the second power to have idea what happened in terms of elastic modulus. We will see later in the summing up slide. Here there is a visual interpretation of what is happening. First row 200 degrees C, second row 200 degrees C, so after thermal treatment, and the last row 400 degrees C. You see what happened in time. This is after thermal treatment. 20 degrees C, there is no thermal treatment. Then after 1 month and after 3 months, you see that you have the closure of the crack. And this is what is possible to see via digital microscope. But if we go further in the detail, we can see also what happened to not the macro crack, but to the micropores and to the nanopores. In fact, this is what is shown here. These are the results from the mercury intrusion porosimetry. And you can see, looking at what happened here, so we are between 10 microns and 100 microns that typically are the micropores and the one that more influence the mechanical behavior of the material. So when we heat at 400 degrees C, we have a large increase of the micropores, but thanks to the healing, we have a strong reduction. And so in the end, the pore size distribution is quite close to the one of the reference specimen. Here we have also some fancy pictures obtained at SEM, so scanning electron microscope, that highlight the precipitation within the matrix. And typically what is important is the radiation of CSH and the precipitation of calcium carbonate. So this is the picture that I was really interesting to show you. This is the curve are the same curve that we discussed in the second slide, I guess. So what we obtained from EC2 and FIB for the hot behavior of the material. The dots represent the results of the experimental test. So now let's not look the rhombus, because the rhombus represents the healing, so the test after 6 months. So we don't consider this. Let's go just to the round and to the square. The round refers to uncracked sample, while the square, the pre-cracked sample. So in general, moving from the round, so just to discuss also the color. Green color represents the flexural strength. Blue color represents the stiffness. I don't like to call it Young modulus, but and the magenta one represents the square power, so the ultrasonic velocity to the second power. This is the decay. We see that it's really interesting that we can see here the round green circle represents the flexural strength. We see that we don't have any loss at 200 degrees C, and we have almost 40% loss of the flexural strength at 400 degrees C in uncracked sample. If we move to pre-cracked sample, we have the square, and you see that we are close to the suggestion, the curve suggested by the Eurocode. This is very important in my opinion. But if we move to the rhombus that are here and here, we see that we have almost a total recovery of the properties. And this is true just for the flexural strength, because if we move to the Young modulus, okay, here I did not represent the recovery, so there are no blue rhombus. But I would like to show you that at 400 degrees C, we are on the line derived from the Eurocode. But at 200 degrees C, we are far higher, without self-healing. Because this test, circle and square, refers to the test just after the heating. Why this happened? Because in this range of temperature, between 0 and 270, 300 degrees C, we have a strong effect of the thermal creep during heating. But in residual condition, we don't have thermal creep. So the effective stiffness that we can measure is far higher. You can see that the magenta symbols are quite consistent with the blue one, because they are trying to represent the same stuff, because the second power of the ultrasonic velocity practically is the Young modulus. There is the only factor that allows to move to one to another one is the density, but the density of concrete, because of heating, changed just 10%, so it's not an impactful parameter. The rhombus, the magenta rhombus, represent the measurement of ultrasonic pulse velocity after 6 months. So we can see that also regarding stiffness, even though it's not strictly stiffness, but is in an index of stiffness, we have a recovery. So I think that this taking in mind what is the difference between hot condition, residual condition, but we can see that we have some positive advices of what happened after the cooling is extinguished. As I said before, if we go beyond 450 degrees C, the story totally changed. I hope to, in the future, to focus also on this aspect, because before 450 degrees C, during the curing after fire, we have a recovery thanks to the formation of the rehydration of the anhydrated particle and to the precipitation of calcium carbonate. After 450 degrees C, or even more, after 500 degrees C, we have the decalcination, the decomposition of portlandite. So in the end, during the residual, during the cooling, I have a worsening, a weakening, because I have the decomposition of the solid part of the matrix. So we have to take in mind that what I said so far, if they are good news, they are valid for the range of temperature between 20 and 450 degrees C. I would like to, okay, here there are the conclusions, but I discussed quite deeply. So I would like to take the chance to thank all the partners that were part of the project, the Smart Things. One that has been funded by the European Union, and so you see it is a very, very big team, and with this I would like to thank you for the attention.